Okay. What is Mohr circle? It is a graphical method of representing the stresses of a general biaxial stress system so that the stress on any given plane or principal stresses and planes can be analyzed. Of course, you might have heard of all these things: general biaxial stress system, principal planes and principal stresses. Okay, if you don't recall what is the meaning of all this, we'll be coming to know in further slides. Okay, what is Mohr circle? First of all, Mohr circle is a graph. You have drawn so many graphs. In the same manner, here also, Mohr circle is a graph. You have x-axis, you have got y-axis, and then graph is there, and then the graph itself is in the form of a circle. That's all. That's all it is. Okay, then it is drawn to represent general biaxial stress system. What is general biaxial? If you take an element from the stressed member and then put the stresses acting on the element, any stress can be replaced by a normal stress and a tangential stress, because even if you have an inclined stress, hope you can understand that if you have inclined stress, means on one face, if you have inclined stress, this can be resolved into a component parallel to the face and then a component perpendicular to the face, and then we can remove this. So this becomes a normal stress, this becomes a tangential stress. And then if you have only normal stress, shear stress will be 0, or only shear stress, normal stress will be 0. That's why general way of representing stress would be some incline, or rather than putting it that way, in a component normal, a component tangential. So this represents a a general biaxial stress system. Okay, next, with normal stress along x-axis and shear stress along y-axis. So it is a graph, first of all. So on the graph, what you have to have on x-axis, you have to have normal stresses, means the 80, the 30 should be measured along x-axis. And then along y-axis, what you have is shear stress. So to say this 25 or this 25, now these are plotted along y-axis, right? Okay, we'll go ahead further. Now the characteristic properties of the Mohr circle. Now what is that you have to bear in mind always while talking about Mohr circle is it is symmetrical about x-axis, right? So if you have the axis like that, the origin O, and this is normal stress axis, right? X-axis, we'll call it as normal stress axis. Now y-axis will be shear stress axis. So the circle can be Mohr circle. When you draw with a given stress system, it can be like that, right? So it can be like that, it can be like that. There are a number of circles that I have drawn, but all of them are symmetrical about sigma axis or normal stress axis, right? You cannot have a circle like that. Mohr circle cannot be like that, or Mohr circle cannot be somewhere there, right? It has to be always symmetrical about x-axis. All these are some or the other Mohr circles representing general biaxial stress system. Okay, further. Here I have a Mohr circle drawn, right? And then a stressed element, one face only the stresses are shown. The stresses are normal stress 80, and then there is a 25. Now, before going further, we'll have to decide what are the sign conventions, right? This is an important part. So here I have decided, you can decide whatever you want, but when you decide something, you have to stick to that continuously. So it is simple to assume tensile normal stresses are positive. So in this case, a face is there and then it is pulling out. Because of that, it is tensile stress. So tensile stress is positive. Even in this case also, it is pulling it out with a magnitude of 80. So it is a tensile stress, normal stress. Now shear stresses with clockwise rotational effect on an element will be positive. So here I have shown shear stresses. So when you have shear stress, and then if you are making a couple out of it, and then the couple is, or the moment of the couple is clockwise, then we'll take those shear stresses as positive. If you have the arrows or the shear stresses trying to rotate it in anti-clockwise manner, it would be negative. Okay. So what is Mohr circle? Every point on the Mohr circle has coordinates sigma and tau. You know that we are plotting sigma or normal stress, we are plotting shear stress, right? Every point will be having a coordinate xy, coordinate sigma and tau. So has coordinate sigma and tau. Every point is sigma and tau, maybe positive, negative combination or some zero, right? So like that. So every point on the Mohr circle has coordinates sigma and tau, and each of these points represent a plane with these stresses acting on them. That's an interesting part. That is Mohr circle. Like here you have a plane with stresses, and this plane is represented by a point on the Mohr circle. That's what is said. Every point on the circle has coordinates, and each of these points represent a plane with these stresses acting on them. That's very interesting. For better understanding, we shall have a point A with 80-25. Okay, now how do you plot 80-25? 80 is measured from origin in x direction or sigma direction. 80, I have drawn that, and then there is 25 in the shear stress direction, 25. So I get a point there. So we'll mark it. I have called it as A. So that is with the coordinates 80 and 25. 80 is normal stress, 25 is shear stress. Now this may be representing point A on the graph, but it corresponds to a plane as shown in figure. So what this point represents? This point represents a plane like that in general biaxial stress system. That's an interesting relationship between general biaxial system and Mohr's. This is the core or crux of the whole discussion. Okay, next. Now let us consider a general biaxial stress system as shown in the figure. So if you have some numerical values, it is easy to understand. That's why I have taken a case where 80-25 on one face and then 30-25 on the other face, right? So sign convention is the same thing, right? Now what observations that you can make in the general biaxial system is always the stress element is in perfect equilibrium. Look at that, 80 this way, 80 that way, it is in equilibrium. 30 this way, 30 that way, it is in equilibrium. And then on vertical faces, if you look at 25-25, it is a clockwise couple, but on the horizontal surfaces it is anti-clockwise couple with the same magnitude. Because of that, it cancels off, and then the element is perfectly in equilibrium. Always whenever data is given, it will be like that only, right? Otherwise it will be moving, it will not be in equilibrium, right? So this is one point. Next, the normal stresses on the opposite faces must be same. So if you have shown 80 here, it has to be 80, obvious. It is supporting the upper statement. Okay. But the stresses on mutually perpendicular faces, in this case vertical and horizontal, may not be having the same magnitude. In the sense, if you got 80 here, on this face it is not necessary to have 80. It can be 0, it can be 30, it can be compressive stress. So anything is possible on the other face. So on one face something is there, opposite face exactly the same thing, but face perpendicular to that will not be directly related to this stress. It has got independence. So it can have normal stress, maybe tensile, maybe compressive, maybe the magnitude itself is 0, quite possible. Observe, the shear stresses on horizontal faces are producing anti-clockwise rotational effect. Horizontal faces, yeah, they are producing anti-clockwise effect now, but the shear stresses on the vertical faces will be complementary to the earlier shear stresses. Here they are having clockwise effect. Obviously they have to nullify that effect. Because of that, they are called complementary shear stresses. Moreover, they must have exactly the same magnitude for equilibrium. Okay. Means sign wise it should be opposite, but magnitude wise they should be same. That is the point. Okay. General biaxial system, the same thing, same sign convention. Here the vertical face is represented by 80-25, and look at the way I have written plus 80 plus 25 because it is tensile. This is clockwise couple, that's why. Now observe, it is true for any vertical face, left side or right side or anyone in between. In the sense, you need not refer to only this face, you can take this face also. I'm telling vertical face, so you can have the plane somewhere there also. But when you consider equilibrium of this element and try to make out what is there on a vertical face, it will be exactly the same once again. Means it will be 80 normal and tensile, and then it will be 25. It will be always trying to rotate the element in clockwise manner. So that is what the statement says. Whether the face is on the left side of the element or right side of the element, or even in case if you take a face in between, it will be same as 80-25 only. So no confusion that if you consider on this side what happens, and then if you consider on that side what happens. As long as it is a vertical face, it will have the same coordinates 80-25, and all these vertical planes are represented by a single point on the Mohr circle. Okay, horizontal face is represented by 30 minus 25. 30 is pulling out, because of that it is plus, it is tensile, and 25 is anti-clockwise, because of that it will be negative. So the point on the Mohr circle would be 30 minus 25, which will be representing any horizontal plane, maybe on the top, maybe on the bottom, maybe in between. So it is true for any horizontal face, top side or bottom side or between, in between. Any horizontal face if you take and then try to analyze for stress along that face, it will be having 30 tensile and then 25 anti-clockwise shear stress. Okay. Now we'll see further. Vertical face is represented by 80-25, say point A, right? Now can we draw or place this point A? Yeah, you take some scale, and then because it is a graphical method, obviously you have to draw it to some scale. Now let us draw on the x-axis. on the y-axis, right? We have origin O, and then this face is represented by 80, 25. So I have 80 distance on the x-axis, 25 vertical distance. I have marked a point A, right? Now horizontal face is represented by 30 minus 25. So I should go 30 on normal stress axis and then 25 on the shear stress axis, that is y axis. It is negative because of that it is below, and it is point B, right? The two faces are mutually perpendicular, vertical face and then horizontal face. In Mohr circle, the 2 points representing these planes will be diametrically opposite to each other. This is the point to be remembered, right? So point A, point B representing horizontal and vertical. When the angle between them is 90 degrees, in Mohr circle they will be standing diametrically opposite. Means if you join the line, if you join the points A and B, that would be diameter of the Mohr circle. Okay, so I have joined, and then the point C, which is on the normal stress axis, C becomes center of the Mohr circle because AB is a diameter. Now it is easy to draw the Mohr circle. So draw the circle with AB as diameter and C as center. So that is your Mohr circle. That's your Mohr circle. Now how to draw Mohr circle is very simple. You have to get a graph and then define sigma axis, tau axis, and you have the sign convention not to be forgotten, right? Simply this represents one point, right? This face represented another point, and because they are perpendicular to each other, they represent a diameter. And then when you have a diameter, this will be center of the circle, because we have already seen that the Mohr circle is symmetrical about sigma axis or normal stress axis. Because of that, the circle can be drawn. Now to find origin of planes, there is a technique which is called as origin of planes. Very simple techniques. We'll see how it can be found in a Mohr circle. Now what is the meaning of Mohr circle, right? OP, origin of planes, is a point on the circumference of Mohr circle such that all the possible planes in stress element will be originating from this point. Anyway, we'll dig into the details here. Here I have a biaxial stress system, right? The point of discussion is origin of planes. Okay, now we have a point on Mohr circle representing a plane with stress 80-25, obviously, right? I have drawn the Mohr circle, right? 80-25, it's already there, need not to be worried, right? Point is already drawn, circle is also drawn for the given biaxial stress system. Now the idea is only to find origin of planes, right? So this face represented by this red line now is represented by 80-25 point. Now that is the point representing that plane. Now what is to be drawn? Draw a line parallel to a plane in the biaxial system to this, through a point representing the plane on the Mohr circle, through a point representing the plane. So this plane is represented by which point? That point. Now through that point, through a point representing the plane on the Mohr circle, draw a line parallel to the plane. So parallel to this face, parallel to this plane, I have to draw a line. Where? Through a point which is representing this plane. Means this is the point. Through this I have to draw a line parallel to this red line. Okay, I'll draw it. There it is. Okay, think it is easy, right? This plane is represented by a point there, so a line parallel to this I have to draw through that point. Okay, then the point where this line intersects the circumference will be known as OP, the point of origin of planes. Means when I draw here, I have got a point. This point is known as origin of planes. So that is what it is. That's all, right? You can say, why consider this plane? Why not you consider this plane, horizontal plane? And the point representing this plane is 30 minus 25. Yeah, you can do that, right? Now the point is here, the plane is there. Now if you draw a line parallel to this, that is horizontal line, through this, you will end up with the same point OP. That's nice. You can take vertical or you can take horizontal, but corresponding point and corresponding planes and then parallel lines have to be drawn. You end up with the same OP or origin of planes. The meaning of OP, now what is that representing, is all the possible planes in the stress element will be originating from this point OP. Now here got the number of planes over here. I'll try to show it here. Okay, now 80, 25. So any plane in between this vertical and horizontal planes will cover all the possible planes. Yeah, you can just see here. Yeah, that is the way how the planes can be, right? Any plane in between will be nothing but that, so that you have covered all. In that 90 degrees rotation will be covering all the possible angle planes. You cannot have anything other than that, right? All the possible planes. Now you can say, if you rotate it in clockwise manner, there will be different planes. Okay, exactly right. They are perpendicular to those planes, that's all, right? So if you are able to cover, look at this range, right, with half the circle, and it is represented by half the circle. The other ones, when you rotate it in clockwise manner for 90 degrees, the other half will be representing. Now I'll show you here. This point is representing, okay, here I have written the corresponding points in the Mohr circle representing these planes change from point A to point B. Here it comes from there to there. All the planes will be either here, there or somewhere. So in between A and B, this way. So those are the points. Look at those are the points representing those planes. Now what is this? So I have told you, when you rotate this plane in clockwise manner, you will be covering another set of planes which are exactly perpendicular to the planes which are now being shown by this line, right? So they will be representing from B to A all the points. That's all. Okay, so next, stress on a given plane. Now, okay, up to this we have done origin of planes. How to draw Mohr circle we have done, and after drawing Mohr circle, how to get origin of planes we have done. Now the next step, we'll discuss this. Now, stress on any given plane. Now we shall have a trial plane M as shown in figure. We shall analyze for stresses on this plane. Okay, now where is that plane? Okay, that is the plane, right? So I have called the plane or the line as M, making an angle of 30 there with the horizontal, with vertical as shown, right? So now this plane, on this plane, if I want to calculate what are the stresses, what is the normal stress, what is the shear stress on this plane, if I want to know, now that can be done right? Using Mohr circle. Already, if you have studied equations, you know how complicated the equations are. Whatever way, that is analytical method, but here it is quite simple. Now, first and foremost, how do you communicate this plane M? Okay, so you can appreciate here that rather than telling the plane makes an angle of 30 degrees with vertical in anti-clockwise direction, how do you define that? That plane makes an angle of 30 degrees with respect to vertical in anti-clockwise direction. So all these things have to be mentioned so that you can clearly communicate that what plane you are talking about. Now it is better if we say the plane is as shown in the figure, because it is a graphical method. Anyway, I have drawn this element and then this plane is drawn here exactly at 30 degrees. So that is the plane, fine. There is no confusion, right? So that's the way how we define the planes. Next. Draw a line parallel to the defined plane on the biaxial system through OP to cut the circumference of the circle at point M. Draw a line parallel to the defined plane, means parallel to this plane, through OP. Through OP I have to draw this plane, right, to cut the circumference of the circle at some M, right? We'll do that. So a line parallel to that and through the point O, I'll cut there. It's easy, I think, right? There it goes, a line. Now here you have got a point. Now that point I am calling it as M, because the plane is M. The plane is represented by a point on the Mohr circle, so that also we'll call it as M. Okay, that is the point M. Now when you got a circle, obviously the coordinates are there, and let us say the coordinates are 60 and 33. I have arbitrarily taken the values. It is not exact one. You have to solve the problem for exact values. Just for explanation sake, I have taken some values. So say it is 60, 33 as indicated. Now what is that 60, 33? It's coordinate of M, and 60, how it is done? It is horizontal distance along x-axis. How it is 33? It is along vertical axis. So that measurement is 33 and this measurement is 60. That's why the coordinates of this point is 60 and 33. But when you have coordinates like that, what is the meaning? The meaning is quite simple, that it is a normal stress, this is shear stress. Now how do you interpret that? The coordinates of this point M will be stresses on the plane M. So on this plane, these will be the stresses. Now we'll detail out. Now I have drawn that same figure, right? To interpret the results, show the biaxial stress system as if it is cut with the plane under the analysis. Means you cut this biaxial system. You can take this element or this element, any one of them, and then show. So I have shown it here, right? So when it is cut, obviously you got two pieces. You can draw this or this. The angle over here is 30 degrees. Angle, if you draw a vertical angle there, it's 30 degrees, or this will be 60 degrees, right? Any one cut part is enough to indicate the stresses on the plane. You can draw this or this, it's one is enough. Note that the stresses represented by the point M had coordinates 60, 33. Earlier I have said that it is 60, 33, both positive. So because of that, hence as per the sign convention, the 60 will be a tensile stress. So I have to draw a line perpendicular to the face and then say that it is 60. If this is the thing, or if this is the element I have taken or the section I have taken, I have to draw a line perpendicular, and then arrow has to be pulling because it is tensile, right? 33 is a shear stress with a direction of rotational effect. I mean, what rotational effect? Clockwise rotational effect, because 33 is positive, clockwise is missing, with clockwise direction of rotational effect clockwise. Okay, here when I draw for this, it will be clockwise for this. When I draw for this, it will be clockwise this way, right? So if you are drawing stressed element and then stresses on the inclined plane, some general plane, then how to interpret the results? Now I'll go back to that. Now you have seen that it is giving you, when you draw a line parallel to this, it is giving you a point with coordinate 60, 33. What is the meaning 60, 33? On this plane, right? If you are referring to this part of the element, it is 60, 33, that is normal and then clockwise. Or even if you consider this also, it is normal, tensile, and then clockwise 33. So that is the meaning. What are principal planes and then how they are found, and what are the magnitudes of principal stresses? We'll straight away go ahead. Okay, the planes without shear stresses are referred to as principal planes. The stresses on these principal planes are referred to as principal stresses. Here I want to make a couple of points. The spelling of principal, 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 important, are main stresses, are main planes. That's why it is PAL, not PLE. Don't make a mistake of writing that way. So they are principal planes, principal stresses. Okay, then one more thing is, any plane, you have studied that there will be normal stress and then there will be shear stress. On any plane, we have seen that there will be a normal which is perpendicular to this, which we have called it as a sigma, maybe tensile, maybe compressive, and parallel to the plane we have seen that there will be a tau which will be trying to rotate the element in clockwise manner or anti-clockwise manner. Accordingly, it will be positive or negative. We have studied. So invariably, rather generally, normal stress and then shear stresses will be there. Now if you find a plane without any shear stress, means there is a plane with only normal stress and maybe a tensile, maybe a compressive, but there is no shear stress, such plane will be referred to as principal plane. That is what the point over here. So very easy to remember, the planes without shear stresses are referred to as principal planes, and the stresses on these planes are referred to as principal stresses. Okay, we'll go to the next slide. Okay, here already there is one biaxial stress element. We have discussed this with the same magnitude, so consider the same biaxial stress element for which Mohr circle is already drawn. You know how to draw. The coordinates of the first vertical plane is 80, 25. It is there here. This is 30 minus 25. It is there. You just join. You get a point on x-axis. Point of intersection on x-axis, you draw the circle. That's how you have drawn. Now further, the origin of planes is designated as OP. You know how to find. Parallel to this vertical plane, which is represented by this point, you draw a line where it cuts the surface, circumference, is known as OP. Origin of planes is there. Now on the circle, can you identify the points representing the planes without any shear stresses? Okay, here every point on the circle is representing some or the other plane, right? If you take a point A itself, there is a normal stress of magnitude 80 represented along x-axis, and there is a shear stress which is represented as y coordinate because it is tau, right? Now if you go on moving this point, here also there is a maximum shear stress, but there is some normal stress. And if you come down here, both the stresses are getting reduced. And then if you come to this point, what is the coordinate? There is some sigma, but there is no shear stress. Similarly, this point is having a magnitude of normal stress right from O to this point, and there is no shear stress. So such 2 points are referred to as principal planes. So they are P and Q. Okay, so S, they are points P and Q on the normal stress axis, where the circle cuts. Those 2 points are representing principal planes. Okay, now the coordinates of these points P and Q be 15, 0 and 85, 0. I have been telling it is not exact values, just I have taken for the sake of understanding. So 15, 0 and 85, 0, let us say. Now the point Q, okay, the point Q with higher stress represents major principal planes, because the P has got 15 and Q has got 85. The higher magnitude point, or the point Q with higher stress, represents major principal plane. So the other point which is having lesser magnitude is referred to as a minor principal plane or minor principal stress. Now can you imagine where and how these planes are on the stress element? Because 85, 0 represents, the point Q represents a plane. Now how and where this plane is? We'll see it. Okay, principal planes. Now you know already that planes originate from OP. That's why we have called this as origin of planes. All the planes should originate from here. And if you are going to that point Q, so that represents a plane M, right, which will be nothing but a major principal plane. Or if you put this plane over here, there, okay, that will be nothing but a plane without any shear stress. Okay, the plane represented by Q is along the line MQ. You can just see here, MQ through OP, that is actually OP to Q. I have extended up to M so that I can refer it to as MQ now. And on the stress element, it can be shown as line MJ on the stress element, which is a major principal plane. Now you have to draw the line parallel to that. You can just see there. If you put that as MJ, so that is nothing but a plane without any shear stress, and then with a major principal stress with a magnitude of 85, and then it is positive value. So major principal stress is tensile, and moreover it is having so much of angle. We can just measure this angle so that you will come to know that with horizontal what is the angle made by principal plane, right? Now similarly, where is minor principal plane? Okay, that is the one. So origin of plane to the point where the plane is represented. So OP to P, that line represents minor principal plane. So where is minor principal plane? It is the plane represented by the point P on the plane, right? and the plane will be along the line NP. The point is P, it is representing a plane and it is along the line NP. N is like MP, MQ we have, like NP. I should have written N here, anyway, it may come, yeah, NP, right, through OP. Now on the stress element, it will be as shown in figure and it will be known as minor principal plane. Now how do you do that? You should draw a line parallel to that there. So that represents minor principal plane, and because you can just see here, we are joining the 2 points on the circumference from diametrically opposite points. That's why this angle is 90 degrees. So to say, the angle between principal planes is always 90 degrees. It is stated here. Note that the two principal planes are always perpendicular to each other, as they are represented by 2 points diametrically opposite to each other on the Mohr circle. And then geometry also tells that if you join such 2 points, diametrically opposite 2 points, any point on the circumference will be getting the angle between those two lines as 90 degrees, right? So this is how to identify from the Mohr circle where the principal planes are represented by the points, and then if you know OP, how to identify the inclination or orientation of principal planes, major and minor both.